said, chi-squared significance tests have been a free response question pretty frequently in the last 5 years. So I don't think it'll be a free response question this year, but it'll, knock on wood. But I think it's definitely going to come up in the multiple choice. It could be a part of a question, maybe on a free response. But so we're going to wrap things up so you can see how the 4 steps might work for a goodness of fit test. And that's what we're doing today. So if we get done early, we get done early today. That's my gift. Okay, so what we're going to do is perform a chi-squared test for goodness of fit. Wednesday, I'm going to show you a chi-squared test of independence. There's a slightly different setup for that one, and that'll be it. But today is goodness of fit, so continuation of Friday. And we're going to conduct what's called a follow-up analysis, where we basically just look at our results and decide which category messed things up for us. So if I remember correctly, I think that was our red M&Ms, but we're going to do those 2 things and just show you how the process is laid out, and that's pretty much it. So you don't need to interact with this per se, but if anyone wants to look at the Jamboard, I'll drop the link in the chat here for today's things. But in the notes, we're on this part. Ooh, I have like a double pointer going on. What's happening there? So we have this page, continuation of our M&M business. And then I dropped the link to the Jamboard. You don't necessarily need that. I'm going to show you how to use the table. So if you want to use the table, let me drop a link to that reference table. Should you want to save your own copy, this is all linked on the week at a glance though, so you can find it later. Okay, so we're going to warm up together with this question, because Friday was a hot second, and frankly, every day feels the same to me at this point. Oh, all right. So we've got this question is just going to give us a little reminder of what we did Friday, and then we're going to kind of formalize what we did Friday into what you'll look at as the 4 steps. So like state, plan, do, conclude, just so you know what that kind of looks like if you happen to get a free response. But like I said, I don't think you will. It's been pretty popular the last couple of years, so they're probably going to do a t-test or a z-test, I think. But anyway, okay, so we have this scenario. This is the check for understanding from Friday's stuff. So if you are in the packet, that's where we're at. So we're gonna look at this. So are births equally likely across all days of the week? So the birth rate is actually dropping thanks to COVID right now, but big surprise. I'm sure it'll bounce back soon. But we took a random sample of 150 births, and we have the following distribution. So which 2 words, there are 2 words in this tiny little description up here that are super duper important. What 2 words do you think are super, super important for this one? Online people, I'm going to give you some time to think. Or call on somebody in the room. Chris, what 2 words do you think are super important? Equally likely. I thought for sure you're going to pick random sample. That one is important too, but equally likely is important. So somebody at home, hopefully you're there, Ben, if you're cooking your eggs. Lillian, what are the words? Do you mind unmuting yourself? What do the words equally likely mean? This is like doing a seance. If you're there, give us a sign. You're with us. Okay. Cheyenne, what do you think the words equally likely mean? Do you mind unmuting yourself? What are your thoughts?
That they have the same probability of occurring.
Yeah, that's excellently worded. Yeah, they have the same probability of occurring. So that's kind of our claim here, is that births, across the country are equally likely to occur. So they have the same chance. So what we want to think about, if there's 7 days in the week, what would our distribution have to look like? I would have exactly a 1 in 7 chance of falling on a given day. So for our hypotheses here, we would say births are equally likely. That we're gonna assume, that's true, I guess. That's what's claimed. What do you think the alternative would be to that? So the original claim is they are equally likely. Kai, what do you think the alternative might be? They are not equally likely, yeah. So births are not equally likely. And that is always going to be the hypotheses for a chi-squared goodness of fit test. It's like it is or it's not. So whatever distribution they're giving you, they're like, we had M&Ms, so we had different percentages for the colors, but for this one, we're saying, they are and they're not. So that's always going to be your thing there. Okay, so we want to get the expected count for each of our outcomes. So we're going to have to figure out what we would expect in each category, so under each day, if they are equally likely. So we're going to have to do some math. So if you have a calculator, people in here, use a real one. People at home, use the one on your Chromebook. But we're going to need the total number of births, which is given there. So that's 150. If each of the days is equally likely, so let's just look at Sunday for example. If there's 150 births and they're all, it's an equal percentage, equal chance on each day, what would I do to figure out how many births would have to happen on each day? So there's 150 across 7 days. Chris, what are you typing in your calculator? Okay, you got 21.4. How did you do that?
150
Yeah, 150 and then divide it by 7. So we expect 21.4 births on Sunday, but it's all equally likely for each day. So we would expect that for all the rest. So we're equally distributing the births across the days. So we expect 21.4 children to be born, decimals are okay, on each of the days. So that's what we're expecting. So if we wanted to get the chi-squared test statistic, this is where we examined how far our observed values, which we have up here, are away from what we expect to happen. So we have to kind of get that for each of our days. So I'm going to use some symbols here. This is technically the symbol for a chi-squared. Chi-squared, that's the letter chi, that's chi. It's not an x squared and it's not chi like the t, so it's chi-squared. Somebody, I don't remember who it was a couple years ago, probably Anthony Wyken, kept calling it chi-squared. Like I'm not a barista, it's chi-squared. Okay, so what we're gonna do, we're gonna take our observed value and figure out how far away it was. We were filling this in on a table on Friday, but we've got our observed value. How far away is it from what we expect? And then it's almost like we're doing out of that difference, like how far off is that out of what it should have been? So it's almost like we're getting like a percentage of how far off it was. But the only mathematical thing we did the other day, let's move that, touch screen, is we squared the difference here, because we don't like negative numbers. When we do things in stats, we just kind of square it and get rid of it. Okay, so what we're going to do, I'm going to show you an example. We've got Sunday, we had 11 births. We're expecting 21.4. We're going to square that. And then we're going to divide that by what we expect. And then we're going to do the next day. We're going to do that. And then we do the next one, so on and so forth. So we're going to go over the shortcut on the calculator again. My calculator is probably going to not work, which is going to be great, but you can put little dots here. You don't have to show like all of these numbers plugged in, and then you can just show the last one. This would count as work as well on your AP test if you had to do that. But basically we're going to add all those up and get our test statistics. So that'll tell us like overall, if we combine all the days, this is where we fall. And I'm going to show you kind of what that means visually here in a second. But let's see if our calculator works. Oh, mine. This computer one's a little wonky. But here's how we would kind of do it. So just to remind you, and this could happen on the multiple choice. So you may have to calculate this on the multiple choice question. I don't know that it's going to be free response and you have to show your work, but like I said, multiple choice is fair game. So we're going to hit stat and then edit, and you've got lists. If your lists ever get full, you can go to stat, and then option 4 is clear list. And you can hit that and then type in which lists you want to clear. So like, for example, in my calculator, I would do second. And if I had something in list 1 and wanted to clear it, I'd push the 1 button, and then I would hit enter, and it would delete the things in that list. So that's if your lists are getting full, you can do that. Okay, but stat edit. I'm going to type in my numbers. So we had 11 births on Sunday. We had 27 on Monday, 23 on Tuesday. We had 26 on Wednesday, 21 on Thursday, 29, 13. And then I get my calculator. We're gonna do trust exercise. I don't know if mine's gonna work, but I reset a few things on mine. It's being stubborn, but we're gonna go back to stat and then test, and then you should have an option for, it's gonna look like an x squared, but it's chi-squared, GOF test. And then you want to make sure your observed values are in, whatever list they need to be in. So mine were in list 1. It should generate the expected values in list 2, but that's probably going to fail again for me. And then degrees of freedom is our categories. So for us, those are days minus 1. So we're going to have 6 for our degrees of freedom. So we've got, 7 days in a week. So, and we're going to calculate, and mine's going to be stubborn and not do it. But if any kind, did you type yours in? Yours worked the other day, didn't it? I feel like it's like, I've got a setting off in here somewhere. I can't remember which one it is. Or it could just be this, broken computer, cheap simulator. It's just not working. Okay, but anyway, I'm going to show you I'm going to also show you on the chart. Oh, I can't do that. Well, okay. Does anyone have it working on their calculator? I really don't know what's wrong with mine on here. Did Chris, were you following along? Did you happen to type it in? Okay, did it work? Great. Did you get a chi-squared number? Perfect. 13.63. Yeah, 63. Okay, I'm gonna have to, mine's probably just because it's a simulator and it's just not, something's not set on mine. But if you do have trouble, with that, let me know on your own computer calculator. Okay, so this is our chi-squared statistic. So here's kind of what this means. We basically, the chi-squared distribution is another set of numbers. It's another type of curve, and we can take a location on the curve and get, an area, chance that something happens, our p-value. So it always starts at 0, and then mine's pretty far out, which probably means I'm going to end up maybe rejecting my original claim. So this is where I'm at, and we always shade, that was poorly written, Fitz, what am I doing? We always shade to the left or to the right on this distribution. So this is my chi-squared value. So the bigger this is, basically the more screwed up your numbers are. So if I'm looking at my numbers, I'm expecting 21 for each of the days, and Sunday's 10 below what it should be. We've got Friday's kind of high as well. So basically, the more off your numbers are from what you're expecting them to be, the larger your test statistic is, your chi-squared number is going to be. And the bigger that is, the more likely you are to probably toss out your original claim. So, Chris, did you get a p-value on your calculator? Great. Ooh, 0.03. Okay, so this is telling us we have a 3% chance with these numbers. We have a 3% chance of obtaining a value, a chi-squared value of this. So if our cutoff point is our usual 5%, am I going to reject, or am I going to fail to reject? What do we think? on this. Tessa, do you have an inkling of what you want to do? We have a p-value of 3%, and our cutoff is always 5%. So do you want to reject or do you want to fail to reject? Do you mind unmuting?
You would reject.
Oh yeah, we're gonna throw that right out. So we're gonna reject our original claim. Because this is a tiny p-value, it's less than what we're allowing. So we're like, ooh, those are unusual results. Anything less than 5%, we're gonna say is sus. So we're gonna reject our original claim and say that births are not equally likely on given days. Babies like to be born clearly in the middle of the week, it looks like. And that is offsetting things enough for us to go, yep, that's, not our claim of everything being equally likely. Everything's a little too far off for us. So now if you wanted to find on the table, table C is given to you. If you wanted to use the table instead of running the test on your calculator, so if you cranked this out by hand, here's how you would use the table. So some people like tables, so I just go over it. So our degrees of freedom are 6, and then I gotta go across this row and find where my test statistic would be, which is about 13.6. So it's gonna be in between here. And then I just go up to here and see that that would have a p-value somewhere between 5 and 0.025. And ours was 0.03 from the calculator. So that's kind of how you can use the chart. It's going to give you a range for the p-value, but that's also acceptable. So you just have to say, I use the table, and this is where my p-value would be between these numbers. But if it were me, I would just crank it out on the calculator. So if you're having issues with that, let me know. But this is the kind of an unformalized process, more multiple choice kind of thinking, I guess, for a chi-squared goodness of fit. What questions do we have? Feel free to drop them in the chat. You can hit the raise hand button. You can just shout at me. Either way, how do we feel about a chi-squared GOF test? I'm gonna formalize a few more things for you, but this is generally the logic thus far. Chris and Kai, do you have any questions? Can that work on your calculator? What's wrong with mine? It didn't work? Okay, I'm gonna have to Google that. Don't know why. There's a setting somewhere. It's probably just flipped and I need to remember which one. I teach just like once a year and then it's like you get back to it, then something doesn't work and you're like, oh, I gotta look it up. Okay, I'll look into that. Okay, so let's go ahead. Let's just formalize our M&M thing. I just want to kind of show you what a few differences are. So if you did have to do a free response for this, which again, I'm thinking, I don't think we will have to, but you will have to probably do some multiple choice answering about it. But let's take a peek. If I'm doing a chi-squared test, so let me move this over. On Friday, we looked at M&Ms. So we organized by color all of our different M&Ms. We had some claimed numbers for our M&Ms. And we then said, the claim was true or the claim is not true. And then we ended up we ended up keeping the original claim. We said the company's claim is true because our p-value is just a hair over 5%. And we had our observed and expected counts. It looks like blue and red were kind of the colors that were messing us up. They were really far off from what we expected. And so when you're doing a free response question for chi-squared, wrong one, you do have a few conditions that you have to check. 2 of them are the same that we've been doing since like January. So for the M&M example the other day, I'm going to kind of formalize it. We have the random condition that always has to be met. So on Friday, did we randomly sample M&Ms? Kai, you were here on Friday. You actually got M&Ms. What a good day. Did we say those were random? Yeah, we did. So we will assume the M&Ms in the bags were random. And then if you were you know, at home you had the simulator, the little dots. 10% is kind of like it's always been. We're going to assume, I think we had what, 400 and some, 480 or maybe, yeah, 480. We're going to assume our 480 M&Ms is less than or equal to 10% of all M&Ms ever made. So those two look the same. The only condition that you may want to remember, and this could come up on a multiple choice, where they're asking you if conditions are met, is what the large counts, because we're not using a bell curve anymore. We're using a chi-squared distribution, which is a slanty curve that gives us some probabilities and stuff, and it just happens to work better in this kind of a problem with categories and things. So for our large counts condition, we have to verify that we can use the chi-squared distribution, and this is the new condition for that. So it says we basically have to have all of our expected counts have to exceed the number 5. Why the number 5? That's a great question. I don't know. Statisticians sat around and went, 5 sounds good. Okay. So we have to examine our expected counts and just state that, yes, all expected counts are greater than 5. So we can use a chi-squared distribution. Or you can say it's valid. Now, if you really want to be, you know, in a free response, you really want to jazz it up. You just want to say which expected count, like use your lowest one. So for us, that's going to be the brown and the red had an expected count of 62.4. You just want to say like, oh, okay, our lowest was 62.4, which is clearly greater than 5. So this just like verifies that, yeah, we do have, you know, it's kind of like your work. That's the only difference on a chi-squared. So if you're doing a situation where you've got categories and you're trying to see if like what you're observing is matching what should be expected for each category, this is to verify that you can do a chi-squared test. So this is the only big difference for that right now. So what we're going to look at, so we already got these numbers from the other day, so I'm just going to move to the next slide. What we want to look at then is what the 4 steps would look like. And I'm not going to write everything back out because we just kind of did some of the things already. But like I said, I don't think this is going to be on the AP exam free response, because like it's been a few times that they've done it. But this is what it would look like if you wanted to do it. And I'm just going to draw in a few of our new parts. So our hypotheses, we said it was the claim distribution is true or it's not true. You want to give your cutoff point just like normal. The name of your test is different. It's going to be chi-squared goodness of fit. So if you see a question where there's a table or there's categories listed, categorical data like colors like we had, or days of the week like we did, then you want to use the chi-squared goodness of fit. I should say 480. Okay, so those are our conditions. And then as far as the doing step, this is what you want to kind of put. This is your formula, which is given to you on the formula sheet. You just have to write it out. Now, as far as your work, you're going to use the calculator, but you do have to show a few numbers plugged in. So just like I did on the warm-up, we want to show, this is the Greek letter to sum things. So to add everything up, so you didn't actually have to put that. But what we would do is just show the first category. So you can put these dots, and then you can show the last category for your stuff. So for us, for our M&Ms, our first category was brown, so it's 60 minus 62.4. So I would just put that in as my first one, so like 60, 62.4. And then that's going to be out of 62.4, and then just go to your last category, and it's on the table, like whatever. So the little dots show that you would be adding up all the other categories in between. It's a nice little trick that they say is acceptable, so we're going to use it. So that would be your work. So that's going to look slightly different than some of the other formulas. And then you can use the calculator or table to get the chi-squared final number and the p-value. The only other thing you want to do is a picture, and don't draw a bell curve. The chi-squared distribution is a slanty thing. And you just want to show for your chi-squared number where it falls on your curve. So for us, the other day, that was the 10.83 on Friday. So I would just show 10.83, and you always shade down every time. It's just how this distribution works. So your p-value is always the shaded part that you're gonna find, off the stuff. And then your conclusion is the same as it's always been. So you just want to look at your p-value. If it's less than alpha, your cutoff point, you're going to reject. If it's greater, you're going to fail to reject. This is significant. This is not significant. So the conclusion logic is all the same that it's always been. It's just the doing step that is slightly different. What questions do we have about a chi-squared goodness of fit question? I'm gonna while you think about that, I'm gonna start a poll. Any questions in here, Chris or Kai? Okay, so we're and people at home feel better drop it in the chat. What we've got here, because this is kind of a long process, so I kind of showed you piecing together how the parts would fit here from start to finish. If you could answer the poll I just dropped, do you want to see another example? My feelings aren't hurt either way. So if you'd like to see another example, click the yes option. Because I have one. Or if you are good, if you're like, yeah, I could probably read this and I could at least logic my way through it, feel free to hit no. So tell me which way you'd like to go, if you'd like to do another example or if you are feeling okay for now. You're currently tied, so if you could keep voting, that'd be good. Find my other example in case I need it. That might be a good idea. Okay. So we've got a couple votes, so I'll let you guys vote. So here's kind of everything we've done. The only thing we haven't totally looked at yet is our follow-up analysis. So I am going to make a note about that. Again, may not have to do this on a free response, but the logic you might have to do on a multiple choice. So the only thing here that we want to do in our conclusion is our follow-up. So if we reject our original claim, we just want to say which category messed it up the most. So if we look back at our results, from the other day, these two categories, specifically the red one, is what probably contributed to us rejecting our original claim because it's so far off. So that's the only other thing you want to add on a chi-squared test is your follow-up if you do reject, like we did here. So the red candies were off by the most is your follow-up officially for that. So, okay, it looks like we have a few votes to try another one. So what I'm going to suggest is, so if you're good right now, you can bop on off. If you want to hang around for another example, I'm gonna do that. So I'm gonna copy and paste here. So if you are good to go, if you understand the things, feel free to have a great rest of your Monday. Otherwise, I'm gonna do another example here quick for those that want it. So okay. Okay, so let's go ahead and do the last question. Let's do another example for those that want it. If you are good, you can bop off. If you haven't voted because you're not at your computer, then I guess you're hanging out for another example. Okay, so here's what we got. A traffic light. So this is the check for understanding under 12.1 part 2. So a traffic light is installed to allow traffic from a seldom used side street to cross a 4-lane highway. So because side streets doesn't allow or doesn't get a lot of traffic, the light is set to provide a red light for the side street 80% of the time, yellow 5% of the time, and green 15% of the time. A resident who must pass through the light several times per day is suspicious that the light is not functioning according to the claimed distribution. So we've got 3 categories of colors. Those are the chances you hit those lights. You set up a trail camera, because that's not creepy. It programs it to snap a picture at 200 randomly selected times throughout the day. So don't avoid this intersection. So here are the results. So this is our distribution of our different colors. So that's going to be important because we have to, based on our 200 lights, kind of figure out what's going on. So let's go ahead and set up our hypotheses. So this one again is going to be just the words. So the claimed distribution is true. And then the alternative to that, the claimed distribution is not true. So the light percentages here is not going to match up with what he collected. So the claimed distribution is not true. Now, what kind of significance level do we want? I'm gonna default it at 5, but if it's not given, you should default at 5. But sometimes it might be given to be 1 or 10%. Okay, so name of our procedure is going to be a chi-squared, and you can put GOF test, or you can write goodness of fit. But in the stats world, the little chi-squared symbol and GOF, it's just understood that GOF is goodness of fit. So then our conditions, we just have to look. Do we have a random sample? Yes, we had a simple random sample of 200 times. So that one's our random condition is good. And then we're going to assume 200 is less than, 10% of all lights, ever. So all the lights of this intersection that ever occur, 200 is, I'm sure, less than 10% of that because it's running around the clock. And then we have to do our expected counts. We have to make sure those are greater than 5. So I'm going to do that up here. So basically, we have these numbers, and we have 3 different categories. We have red, yellow, and green. So we have 200 lights, and we expect 80% of the time the light to be red. So if I have 200 lights that I've taken, timed like snapshots, then I expect out of the 200, 80% to be red. Because that's what the claim is. For yellow, I expect 5%. For green, I expect 15%. I just need to know, what these numbers are. So you can just punch that in on your calculator, essentially. But if we do that, we're going to have math here. 160 is 80% of 200. And then math 10 is 5% of 200. I think that's right. And then 30 is going to be our expected amount for green. So all we want to do for our last condition is just make sure that everything we expect is greater than 5. So we just want to state that. So all expected counts are greater than 5. And so we would specifically want to list the lowest one. So like yellow is the lowest, but 10 is still greater than 5, so we're good. So then what we want to do is plug in our information. So our chi-squared formula is always our observed thing minus our expected thing divided by the expected thing. And then I just have to plug in, this is a pretty short one, I guess, with all of my numbers. I only have 3 categories, but I want to just type or put in what our things are. So for red, I've got 173, and I would take away what's expected and divide by what's expected. So that's the 160, where 180 came from, 160. Plus dot, dot, dot. And you can do the last category. You could list all 3 of these because there's only 3, but I don't want to. So, okay, so then we do the green one. So 30 minus, green, we had 14 minus what's expected, which was the 30. Square it divided by 30. So then I could do this one on my calculator because there's only 3 categories, but you can just use the GOF test again if you want. I did have this example ready ahead of time, just in case I needed it. So I did punch this out already, and I got 10.94. So on my distribution, it would, it starts at 0. 10's pretty big. So I might end up projecting, but what we want to do is find our p-value using the test. So I did this ahead of time, thankfully. I don't know what's wrong with my calculator on my computer, but the p-value for this one off of my calculator from home to get this number, which is super tiny. I could also look at my chart if I want. So I have 3 categories here. So the degrees of freedom on this test is going to be 2. So on my chart, I could go to row 2, and then I would go over until I find roughly 10.49, which is going to be in between these 2 numbers. Or just go up here. And this is a really tiny p-value range, which is less than 5%. So either way, you're going to end up rejecting things. So on this one, we are going to reject the null because our p-value is less than 0.05. So the claim distribution, I'm running out of room, is not true. So basically, you're getting screwed on your traffic lights in this town. So whatever they're claiming is not actually happening. So what we would want to look at is which light is off by the most. Which category is throwing things off the most. So if I'm eyeballing this, yellow was off by 3, so it's not going to be yellow. Red was off by 13, and green was off by 16. If I'm looking at what we got versus what's expected, so I'm going to say for my follow-up, because I did toss out what people thought was true, I'm going to say green contributed, run out of room, to this, because it was a difference, had the greatest difference between what was expected and what we actually got. So that would be the 4 steps kind of laid out again, and this was all recorded. So if you want to go back and ever watch this part of the lesson, just to look through another example, you may do that. So that is the last example.